Do I start? Okay. Okay, so today we will start with the L2 Hodge theory part. Okay, so what I will do today is to introduce these harmonic forms, and I will start to doing the Hodge theorem about harmonic forms, and after I prove that, it will be I think that maybe one more class to prove the Hodge decomposition theorem. Okay. So, okay. So let X omega be a Hermitian manifold. Okay, and consider, so we know that if we write, if we take any point and we take any chart around this point, so we can take coordinates. Let's Cj equal to xj plus I yj be a coordinate system. So we know that in coordinates we can always write this 1-1 form associated to the Hermitian metric as I over 2 the sum ij equal 1 to n of hij dci which dcj bar. Right? We already discussed that in the previous class. So this form induces, so this 1-1 form induces a volume form. Right? This is dB. By definition, it is omega to the n over n factorial, and it's exactly I over 2 to the n, the determinant of the matrix induced by H times the Z1 wedge, the Z1 bar, and the Zn which the Zn bar. Okay, and this is equal to the determinant of Hij times the x1 wedge the y1 until the xn wedge the yn. Okay, and so since this is a Hermitian matrix, we know that this determinant is positive. Right? So in particular, this form is always positive, you know, and so the integral of this thing is different from 0. Right? Right? So, so in particular, we have a, proposition that it's a corollary of this observation. So let X omega be a Kähler manifold, a compact Kähler manifold. Then for every, well, let's say h, so omega to the k is different from 0 in the 2k, the Rham cohomology group of X, and in particular this guy is non-zero. Okay, for every k equal to 0 up to n. Okay, so this is another condition for a manifold being Kähler. I mean, this is a necessary condition for being Kähler. The even degree cohomology groups are non-zero. Okay. Well. Okay, so now we will start with the L2 part of Hodge theory, and in order to do that, we have to introduce a metric. Well, in order to introduce harmonic forms, we have to introduce like an inner product, an L2 inner product, in the space of forms, of differential forms. Okay. So now consider a coordinate system such that, let's say it's C1 to Cn, such that the derivations, these guys, are a unitary frame or a orthonormal frame of Tx, okay, in every point. You can always choose these coordinates, okay, with respect with the metric. I mean, we're taking a Hermitian manifold X, okay. Okay, so this induces a metric on the cotangent bundle. First of all, it induces a metric on on the cotangent. This is a metric on the cotangent bundle where this dC1 up to dCn is a unitary frame, is an orthonormal basis. Okay. Well, this frame, it induces also a frame on the complexified cotangent bundle, and also it will induce a frame on the exterior products of exterior powers of the complexified cotangent bundles. So it also induces a frame on this that is just taking this dz to the I wedge dz bar to j, where this I plus j equal to k, and so we have an induced metric on this bundle, making this frame a orthonormal frame, right? Okay, so in coordinates, this matrix is nothing else than taking so the product of u and b, it will be exactly the sum of this I plus j equal to k of u ij times b ij bar, where this u is equal to the sum of I plus j equal to k u ij dci, which the zj bar, and b is the same thing, bij dzi, which the zj bar. Okay, it's nothing else than this product. And so using this inner product, we can define an L2 product on the sections of the space of sections of this bundle. So definition. So let x omega be a Hermitian manifold of dimension n. Okay. So the L2 product on the space of global sections, global K forms, is by definition the following product. So UB L2 is defined to be the integral over x of u times b dB, okay, where this dB is the volume form. For every u and b omega k x infinity x. Okay? So using this L2 product, we can define a very important operator that is called the Hodge star operator. So the Hodge star operator is by definition an operator that goes from omega k, I don't know, let's say omega pq x infinity of x to omega n minus p n minus q x infinity of x. Okay, and is the operator such that the product of u b dB is equal to u wedge the star of b. So it goes from, so it will be for every u in omega pq x infinity of x. Right? Okay, and this map, I mean, this is well defined, and you can in fact define it explicitly in coordinates. So in coordinates, it is just the star of b is equal to the sum of ij sigma ij v ij bar dc I complement, which dc bar j complement, where this sigma ij is a number, complex number. In fact, it has norm 1. In fact, it's a sign times a power of I. It's a power of I. Okay. Such that, so this number is characterized so this number such that sigma ij dc to the I dz to the j bar, which dci complement dc bar j complement is equal to db. Okay, you have to reorder this thing, and that's why there will appear some sign here, and also, well, you have this power of I appearing in this part. Okay. So if you define it in this way, you will see that when you do the wedge product of this with u, you will get exactly this, right? Okay. So, in consequence, in particular, if we compute the double star, I mean this star operator is an isomorphism, okay? And why? Because if you apply it twice, what will you get? So you will get the sum ij sigma ij the star b bar ij dc I complement dc bar j complement. And do you understand what I mean by I complement and j complement, right? It's just the complement in the set from 1 to n and order, I mean increasingly. Okay, and what is this? This is the sum ij sigma ij bar of sigma I complement j complement b I complement j complement dc I complement which dz bar j complement. Okay, and so since this number, I mean this sigma I complement j complement of dc I complement which dc bar j complement which dci dcj bar, this is equal to what? This is equal to, if you take these two guys and put them in front of these other two guys, you will get, this is exactly this is sigma I complement j complement times minus 1 to the size of I plus the size of j is p plus q times 2n minus p minus q times dc to the I dc bar j dc I complement dc bar j complement. Right? And this, by definition, this is equal to dB. Right? So this relation implies that well, let me I complement j complement. Is this right? Correct? Yeah. So this relation implies that this sigma I complement j complement is equal to minus 1 to the p plus q sigma ij. Right? And so whenever you take this product, this will be exactly equal to minus 1 to the p plus k b. Right? So in particular, the inverse of the star is minus 1 to the p plus k, p plus q, the star. Right? So you have this identity. Okay, why is this operator so important? It is because it will be, we will use it in order to define adjoints of operators acting on the space of differential forms, right? So we will have differential operators or some other operators acting on this space, and we want to produce the adjoints of these operators, adjoints with respect to the L2 norm. And we will produce them explicitly. We won't have to use any functional analysis to prove that they exist or anything. We can define them using this star operator explicitly, and it will be like the formal adjoint. Okay. So for instance, so here another definition, I mean, in terms of the star operator, we can define the adjoint of the partial bar. That it goes from omega p q plus 1 x infinity x to omega p q x infinity of x. And how do we define it? It's just define it in this way. It's just this map. Okay? And it is the adjoint because for any pair of differential forms, u p q minus 1 x infinity in a p q minus 1 form, and b a p q form, we have the following relation. So So the product of partial bar u with b in L2 is exactly the integral over x of partial u wedge the star of b, right? This is equal to so if we derive, if we just, this will be exactly what the partial of u wedge the star of b minus, so maybe I will write it here. So it's the integral over x, the partial of u wedge the star of b minus the integral over x of what? So the degree of u is p plus q minus 1. So it will be minus 1 to the p plus q minus 1 u wedge partial of star of b, right? And so this form is what? B is a PQ form, a star of B is an n minus p, n minus q form. So this wedge is an n minus 1 form, right? This is n minus 1, right? So in particular, this is equal to the d of u wedge star b, right? And so by Stokes, this is 0. By Stokes' theorem, okay? And so we have that this is exactly minus 1 to the p plus q, the integral over x of u wedge partial bar star of b. But, b is a pq form, a star of b is a n minus p, n minus q form, and the partial of this is an n minus p, n minus q minus 1 form. No, plus 1, right? And so if we apply two times the star operators here, we will get minus 1 to the n minus p plus n minus q plus 1. That it is p plus q plus 1, right? So we will get, this is exactly minus the integral over x of u wedge star partial bar star b. Right, and this is just equal to the integral over x of u wedge the star of the adjoint times b, and this is the L2 product of this, right? Cool. Okay, so why are we introducing this adjoint operator? Is because we want to define Laplacians, okay? But first of all, I will motivate the definition of the Laplacian with a proposition. So proposition so a form delta closed form PQ form. So it is of minimum norm, L2 norm, inside its class in the Dolbeault cohomology group, omega plus delta bar omega p q minus 1 x infinity x. This is a class inside the Dolbeault cohomology group. If and only if the partial bar adjoint of omega is 0. Okay, so proof of this proposition. So you don't have any questions? No? Okay. Yes? Is it clear? Everything is clear up to now? Yeah? Okay. So how do we prove this? So, well, in one direction. So let's go this direction. So suppose we have this omega and it is of minimum norm inside this set. Okay? So consider for t in R, so take, for every b in omega p q minus 1 x infinity x and any t in R, we will have that the norm is squared, right? We know that the norm squared is differentiable, right? So t partial of b squared, we know that it has a critical point at 0, right? So the partial of this in t equal to 0 is 0. Right, and also if we take another path, that is just taking omega plus I t partial of b squared. Right, this is just because it minimizes the norm to the norm squared, and the norm squared is differentiable. Okay, and so if we compute this norm, we will have that the derivative of the norm of omega squared plus t squared, the norm of partial b squared, plus the product of omega and t partial b L2 plus the product of t partial b omega L2 is 0 when you derive it and you take t equal to 0, right? And on the other side we also have that this the same thing, right? And here we have plus t squared, or must be a square, and here we have an I, right? So whenever you take this out, minus I omega t d L2, you will get this t outside here, this other t is also outside here. Here you will have t outside, and here you will have it IT this is also 0, and so well, what this implies is that these two things are 0, right? Omega partial b equal to partial B omega L2 B sort 0. Right? So in particular, we know that B times the adjoint of omega in L2 is 0 for every B that we take. So we can take B equal to this, and we conclude that the norm of the partial omega squared is 0, and this implies that this thing is 0. Right? And in the other direction, so conversely, so if the adjoint of the partial bar of omega is 0, and we take any B P Q minus 1 form such that the partial bar of B is non-zero, then the norm of omega plus partial bar of B squared is equal to what? It's equal to the norm of omega squared plus the norm of partial B squared plus 2 times the real part of omega times, well, we will take it partial bar of B times omega, right? And this is just it's 0, right? I mean, this is B times partial bar adjoint of omega, and this is 0. And so this is strictly bigger than the norm of omega squared. Okay? And so in consequence, the element minimizing, I mean, the elements of omega pq x infinity of x such that representing the how do I say this? Well, okay, the elements representing the representatives corresponding, yeah. Corresponding to the representatives of minimum L2 norm in each class of the dot-Bock homology are exactly the ones such that the partial of omega is 0 and the partial dual of omega is also 0. Right? And this is equivalent to that the Laplacian of omega, that is by definition delta bar adjoint plus delta bar adjoint delta bar, omega is equal to 0. And why? This is true because we have the following identity. So since so the L2 product of the Laplacian of omega times omega is the same thing as so it is partial bar omega L2 plus partial bar partial omega L2, and this is exactly just, well, you will have the norm partial bar dual of omega squared plus so here you will take the complex conjugate of omega partial bar dual partial bar omega L2, and this is partial bar omega L2 bar, and this is the norm squared bar, but it's the same norm. Okay, so it is the sum of the two norms squared. So this is 0 if and only if both things are 0, right? Okay, so this operator is called the Laplacian operator. Maybe we'll call it the delta bar Laplacian. Okay, and a form, and we say that a PQ form is harmonic if it's in the kernel of this operator, right? Okay, so these are the harmonic forms. So we denote this space, the kernel of the Laplacian, we denote it like this. Okay, so it's the curvy H, the math calligraphic H. Okay, so if we consider any harmonic form, I mean, is it everything is clear? Yes. Okay, So we know that the harmonic forms are exactly the forms where the partial bar and the dual of the partial bar cancel on these forms, right? So in particular, we have a natural map that goes from the space of harmonic forms to the Dolbeault cohomology group, right? Since each harmonic forms is partial bar closed, right? And furthermore, this map is injective. Why? So if you have here an omega and it goes to 0, I mean if omega is equal to partial bar of something, right? And we know that it is harmonic, right? So in particular, the norm of omega squared is what? It is the wedge L2 of omega with the partial bar of B, right? And this is equal to the partial bar adjoint of omega with B, and this is 0, right? And so omega is 0. So this map is injective, and what we have to prove, in fact, one of the main theorems that we need to prove in order to prove Hodge decomposition is that this map is in fact a bijection. I mean, every Dolbeault cohomology class has a representative that is disharmonic. Okay, so each of these, I've erased that, but each of these classes has an element that attains the minimum of the L2 norm, right? That's not obvious. Okay, so in order to prove this theorem, we will have to use some functional analysis tools that are very strong, in fact. In fact, they're quite hard to prove. So I won't prove it. In fact, I will just use it. And it's about elliptic operators on a space of sections, infinity sections of vector bundles. Okay, so in fact I won't even explain what it is an elliptic differential operator. I will just tell you that the Laplacians are elliptic operators. Okay, so the theorem is the following. So I didn't thought in a reference for this. I mean, I think that in Boissin's book, this theorem appears. She just used it. She doesn't do any sketch of proof or nothing about this. But in the Miley's notes, there are some notes of Jean-Pierre de Miley that it's called L2 Hodge theory, or in French, I don't know. And there you can find something like a sketch of proof, but he also reduced the proof to some other theorems, PDE theorems, that are quite hard to prove. So let E and F be two Hermitian vector bundles over a complex manifold, a compact complex manifold, M, such that they have the same rank. Okay. and let P from the infinity sections of E to the infinity global sections of F be an elliptic differential operator. Okay. Then we have the following things. Then first, the kernel of P, it's finite dimensional. I mean, the dimension of the kernel of P is finite. And 2, so the image is closed with respect to the L2 norm here. I mean, in the same way that I explained for the case of the exterior products of the cotangent bundle, the matrix in E and F, they induce matrices in this space. I mean, an L2 metric here, an L2 product, right? So with respect to the L2 product of this, right? This is closed of finite codimension. Right? And furthermore, if P star is the formal adjoint, then there exists a decomposition so infinity sections of F are decomposed as a direct sum of the image of P plus the kernel of P dual. Okay? And this is orthogonal, which is orthogonal. This L2 product. Okay? So the example is that P equal to this operator is elliptic. Okay, I won't explain what, I won't give you the definition, but this is something that you have to believe in. And it's not hard to check if you know the definition, but the definition uses a lot of machinery. I don't want to explain it. Okay, so I don't know what time is it. Okay. Well, so using this theorem, well, we just applied, we can get the following result. So this is a theorem of Hodge. So let X be a Hermitian manifold. Compact. Then, so first of all, the dimension of the harmonic forms is finite. And second, the orthogonal projection from HPQ to the harmonic forms is well defined. And there exists a unique green operator a unique green operator G from omega PQ x infinity of x to omega PQ x infinity of x such that it is 0 over any harmonic form. It also commutes with partial bar and with the adjoint of partial bar. And also it decomposes the identity. Identity is equal to this projection plus the Laplacian applied to G. Okay, so this is Hodge theorem. So what is the proof? So the proof is not too hard after we have the theorem. It's okay? So the proof, well, the first, well, apply the previous theorem to E equal to F equal to the wedge P T10 X dual times Q T01 X dual, right? And P equal to the Laplacian, right? So if we apply this, so one follows immediately, right? The kernel of P are the harmonic forms, so it's finite dimensional, right? And now how do we do the second part? And so two. So the first part is to so note that the Laplacian is an adjoint operator. It's a self-adjoint operator, right? And so we have that the PQ forms decompose as a direct sum of the image of the Laplacian plus the harmonic forms, right? So you can write any PQ form as a sum of something Laplacian of something plus something harmonic. Okay? So in particular, you have well-defined this projection, obviously, right? You have, so the first part is well-defined, and now we have to define the green operator. So for any omega in a global PQ form, we can write omega as a sum, right? Laplacian of something plus something harmonic, right? Where this is in H PQ partial bar of X. So how will we define the Green's operator of omega? So in particular, so we have this. Note that the Laplacian, when you restrict the Laplacian to the image of the Laplacian, it will go to the image of the Laplacian, and it will be an isomorphism. This is an isomorphism. Why? Why it is an isomorphism? Because so whenever you know that if you restrict to the whole space, it will be surjective to its image, right? But this part will go to 0. So if you restrict to here, you will have a surjective map, and the kernel of that map will be exactly the intersection of this with this, that it's 0, right? So it is an isomorphism. Right, so in particular, we know that this Laplacian of phi is equal to the double Laplacian of something. Because this is here, that implies that it is equal to this for some b, right? And so we define G of omega to be the Laplacian of b. Okay, and so we have to check that this is well defined, right? So if we pick another representative of this decomposition, and if we pick, another element here, a phi tilde, such that the Laplacian of phi is equal to the Laplacian of phi tilde, and we pick another b tilde such that the double Laplacian of b tilde is equal to the Laplacian of phi tilde, we have to check that the Laplacian of b is equal to the Laplacian of b tilde, right? So if Laplacian of phi is equal to Laplacian of phi tilde, and the double Laplacian of B tilde is equal to the Laplacian, well, to this same thing, phi tilde. Then, so the Laplacian of B tilde minus the Laplacian of B, it is 0. Why? Because when you apply the Laplacian to this, it will be 0. Right? But we know that this guy is in the image of the Laplacian. And when we restrict to this image, we know that the Laplacian is bijective. So in particular, this implies that the Laplacian of B tilde is equal to the Laplacian of B. Right? So it is well defined. It is well defined, and certainly by the way we define it, the Laplacian of G of omega, it's the double Laplacian of B, that is the Laplacian of phi. Right? And so we know that this decomposition implies this other decomposition. Okay? And how do we get that it maps every harmonic form to 0? It's because it is already well defined, right? So since it is already well defined, whenever we take here omega harmonic form, it will be 0 plus something harmonic, because the composition is unique. So in particular, it will be the Laplacian of 0, and so the green operator, it will be 0. Right? And to see that it commutes with partial bar and with the adjoint of partial bar, you just have to check that the partial bar and the adjoint of partial bar commutes with this Laplacian in each step, and that's obvious. Okay? Well, so that's the proof. Okay. Do you have questions? No? Too technical? Too... Okay, so corollary of this is that we can prove what I claimed before. We have this isomorphism. So corollary, the natural map that takes every harmonic form to its Dolbeault cohomology class. It's an isomorphism. And the proof is just, we just need to check the surjectivity. We already checked the injectivity. So if omega, it's a PQ form such that partial bar of omega is 0, then we know that this omega is equal to partial bar of G of omega plus the projection of omega in the harmonic form, in the harmonic forms. Right? And so, in particular, we know that G commutes with partial and with partial bar. So we know that this omega will be equal to partial bar of partial bar adjoint of G of omega plus partial bar adjoint of G of partial bar of omega, that this is 0. plus the harmonic part. Right? So in Dolbeault cohomology, omega is equal to its projection to the harmonic forms. Right? Right? So another corollary that we can derive from this theorem, it's a version of Serre duality. So this is Kodaira-Serre duality. Okay. So let X be a compact complex manifold of dimension n. Then, so first of all, the Dolbeault cohomology groups are all finite dimensional. The top forms are one-dimensional. And this map is an isomorphism. And the third part is that we have a perfect pairing. Given by the wedge. It's non-degenerate. Okay. So in particular, we have a correspondence between this group and the dual of this group, right? This is Serre duality. So the proof, so the first part is just that this guy is isomorphic to this other guy. So you fixed, so we previously fix a metric, a Hermitian metric. On X. And so we have this iso, and we already know that this is finite dimensional. So the first part is this. The second part So take any omega here, n form, global n form. So we know that, so such that obviously it will be closed. We know that this omega is a function times times the volume form, right? For some f as infinity function, right? Right? And so again, we know that this space is isomorphic. It has only one harmonic representative, right? So we can assume that omega is harmonic. That it is the harmonic representative of its class, right? Right? And what does that mean? I mean, that means that the partial bar adjoint applied to omega is 0, right? This is 0. And what is this? This is just minus the star operator, partial bar star operator of omega, right? And if you look at the definition of the star operator, you will see that the star operator is taking just the adjoint, no, the conjugate of f times a number, a constant, right? Then you will take the partial bar of the adjoint times a constant, and then you will get the bar of that thing. So at the end, it will be equal to a non-zero constant times partial of f, right? Equal to 0. Right? So this implies that the f is anti-holomorphic global function, right? But you don't have any global anti-holomorphic function on a compact complex manifold. So this implies that f is constant. Right? And so in particular, we know that this is one-dimensional, and it's generated by this guy. And obviously, the only thing that you have to check to have this isomorphism is that the integral of this guy is non-zero. And we know that it's positive, so it's non-zero. Right? So for the final part, so the last part, so we just need to check that it is non-degenerate, and it's quite easy, because if omega it's well, first of all, we have to see that this map is well defined, and that's not too hard. I mean, just you have to add something that it's exact, and do the wedge and see that it is exact, assuming that this guy is closed. It's easy. So it's well defined, and so we can restrict ourselves to the map taking only the harmonic representatives, right? So if we take an omega that is harmonic and non-zero, and then well, maybe we'll do this here. Then the wedge, I mean the product of omega, which the star of omega, we know that it is equal to omega omega dB, right? And so we know that this is non-zero, right? Because the integral of this is the L2 norm of omega that is non-zero, right? And so the only thing that we have to check is that this guy, the star of omega, is inside the Dolbeault cohomology, right? So this is non-zero. And we know that, so we have to check that I don't know, that partial bar of the star of omega is 0, right? Because the star, you remember, the star is defined over all the PQ forms, right? So in principle, the image of the star is not, the star of omega is not necessarily delta closed, right? And why is this true? Omega is harmonic. This is just like this is like a sign, right? This is a star, partial bar, star, omega times a sign here, right? Omega is a PQ form, the star is n minus p, n minus q, n minus p, n minus q plus 1. So it is times minus 1 to the p plus q plus 1. And this is the partial bar adjoint of omega, and this is 0. Right? And so the product is non-degenerate. Cool. Okay. Well, just a remark is that we can do the same thing that we have done up to now. I mean, we start to work with the adjoint of the partial bar, right? We could work with the adjoint of D, the whole D defined over the whole K forms, the whole space of K forms, right? We can do exactly the same thing. I mean, we know that the star operator, we define it for PQ forms, but we could define it for K forms, right? In exactly the same way. I mean, we can take U B dB equal to U wedge star B, where now B is a K form, U is a K form. So the star of B will be a 2n minus K form, and so on. So we can define the star operator. Using this star operator, we can define the adjoint of the operator D. We can define the D bar, the D dual, the D adjoint, and we can define the Laplacian with respect to D, right? To be D plus, right? And so we can, this operator will also be an elliptic operator. Now not on this vector bundle that is the wedge of P times the well, you know, it will be over this omega k of T C of the kth exterior power of the cotangent complexified cotangent bundle, and it will be also elliptic. So we can also apply the same theorem that we applied in order to get the theorem of Hodge, and we can prove that in fact we can prove that. So we can define. I mean, we say we can define this H k d of x to be the kernel of the Laplacian with respect to d. So these are the harmonic k forms, right? And we can prove that this map, again, we have, so omega is harmonic if and only if d omega is equal to 0 and the dual of d omega is equal to 0. And again, we have this map there is now going to the whole de Rham cohomology group, and it's an isomorphism. So in the de Rham cohomology, we also have that each class has a unique harmonic representative, right? And we can also obtain a corollary in this same spirit as Kodaira-Serre duality, but what we will get in this case, we will get that the dimension of the de Rham cohomology groups of a compact complex manifold are finite. We will get that the top forms are of dimension 1, the same integration map, and we will get the Poincare duality here, right? The k forms times the 2n minus k forms, the wedge is not degenerate, right? So we have this with this fact, and we also have the Poincare duality. Okay. So this is all. Okay. So in the next class we will try to relate these harmonic forms with these other harmonic forms here, right? These PQ harmonic forms. In order to do that, what we have to do is to relate the Laplacians, the two operators. I mean, this Laplacian with the Laplacian with partial bar, and these two operators are not related in general. And this is where the Kähler condition will be extremely important. Okay, have questions?